Okay, so here we are on the 30th of July. Homework set number 14 is the one that's due for today. And we have a couple more, and then, yeah. So if we look at the assignment section, well, here, let me find that here. If I go to Blackboard and I look at this course and I go to the assignments, what you'll see is that it says publisher site right here. But notice that it has stat homework number 15, which is not on the publisher site. Okay. Stat homework 15 is just a thing on Blackboard. It says 16, but it's actually 15. Sorry, but it's homework set number 15, and it looks like this. Okay. So what's happening here on homework set number 15 is going to be just this sheet of paper, okay? And answering the questions, you don't have to turn in this sheet. It might help you if you did. But all I'm looking for are your answers written out, like a regular old homework problem thing. And you're going to hand this in on Wednesday, okay? And then I'll grade it, and then I'll put the grades onto the publisher site, so they'll be in the same place as all the other stuff. Okay, so when it comes to our schedule here, and it says homework set number 15, it's not online like the other things are. Homework set number 15 is in the assignment section, and when you click on it, it just shows you a couple of sheets here. You look through those, you do them, you get the answer. Okay. So, any question about that right away? Okay. So then, when we go to the schedule, we do see that we had a test last week, and I have all those graded here, and I can hand them back to you. Before I do that, I think it's important to note that most people did okay. A few people had trouble. A few people had a lot of trouble, but in the main, most people did okay. There are a couple of people who need to be making plans for retake of earlier exams, okay? Not necessarily this one, but earlier ones. Those things need to be done pretty soon here, okay? So that we can get everything squared away for your actual grade at the end. But for right now, I'm going to hand these back to you, and then we'll talk. So, Danielle. Okay. Oh, yeah, I did. Oh, I got 3 off right here.
Did you hit the right critical?
Now, there were some people who did relatively well through a lot of the tests and then really messed up on the last one. And other people had various problems on the other parts, and then the last one went okay. So crazy how that happened. Right? Purpose of the confidence interval is to measure something about a population, or to use a sample to measure something about a population. That question will appear on the next test as well. If you don't have that memorized yet, you should. And I'll probably be asking you every day between now and then, what's the purpose of the confidence interval? Use a sample to measure something about a population. That's question number one. Most people did okay regarding the confidence interval questions. Number 9, by the way, I decided to cross that one out. P-value question. We talked about it a few times, but we didn't really go over it in enough detail for me to feel good about it once I got it on there. So I crossed it out. If you got it right, then you got extra credit. But we'll talk more about that later. So let's see. I suppose it might be worthwhile for me to put some things up here on the board. Some people had some trouble with this, but most people got it okay. If we're talking about a proportion, then most of the time we're using z-scores. Talking about the mean, we use t. And when we're talking about the standard deviation, we use chi-square. So then if we're looking for critical values and rejection regions for a standard deviation problem, then that would be a chi-square. So, number 6. Sorry. Yeah. So does anybody have any question about anything on page 1? You will be seeing confidence intervals, hypothesis testing, null and alternative hypotheses, test values, and critical values on the next test as well. So if there's something that's missing here, we need to kind of get it fixed. Now, possible. Right? And like I said, most people did okay, so maybe you don't have any questions. If we go on to page 2 then, and specifically question number 16. When I say on here do an appropriate hypothesis test, then what that would mean is you do null and alternative hypotheses, you find the critical value, find the test value, you make a decision, you summarize it, and write the conclusion. Okay, all those things are in there. Some people just had a lot of trouble with the thing. I guess probably the biggest problem was in the critical value. A number of people had the null and alternative hypotheses correct. Null and alternative hypotheses. U is equal to 4.6. U is less than 4.6. Well, if this is your alternative hypothesis that it's less than, then this has to be a left-tailed test. And if we're talking about the mean, we're talking about the t-distribution, which has 0 in the middle, and things to the left are negative numbers. So if you say the critical value is 1.746, if that's your critical value, that's good as far as it goes, but it's not actually what's happening here. This is a left-tailed test. It's a left-tailed test. That means we need to be over to the left, and that means that this would be a negative number. So this would be negative 1.746, and then this is where you put that in there. There were a few people that had trouble when you're supposed to make a picture and you do your rejection region. They took this to be 1.746 positive, and then they shaded in everything over here. Rejection regions never look like this, okay? Rejection regions are not the big area here. Rejection regions are just the tail of the distribution. So then it would have to be a negative number here. And again, we talked about that a couple of times, but understandably, I mean, there's a lot of stuff on here, right? So maybe you missed that part. But what I found, which was, I think, this is just my teacherly opinion, okay? If you recognize that you've done the wrong picture for your test value, let's say your test value comes out to be a negative 1.499. If you had a positive 1.746 and your test value comes out to be a negative 1.499, that would generally seem to be an indication that something's wrong, okay? Something's not right about the situation. So then you would have a choice, okay? Which thing do you think is correct and what would you do about it? Okay? So some people, after seeing that their test value was negative, they just kind of ignored the fact that this was a positive number and they just switched it. And they said, it must be a negative. That must be what I'm supposed to do. And that is the correct thing to do. When you look at it and you say, oh, I drew this picture, but I got this test value. This picture is wrong. It's the correct picture. Test value is right here, negative 1.499. Okay? However, if you say, well, I got the critical value to be this positive number, and I got the test value to be a negative number, it's possible that you would say, well, this negative number must be wrong. I must be doing it wrong, so I'm going to make it into a positive number. But that's not really good, because this is t is x bar minus mu over this. X bar is 4.2, mu is 4.6. So this should come out to be a negative number. If it's not a negative number, then you made it wrong, okay? So part of the process here is that if you recognize that something's wrong and you go back and you say, okay, what needs to maybe be fixed in the situation? And to simply say, well, this is positive and this is negative over here, and they don't match, if you just say, oh, well, that's not a problem. Well, it is a problem because they're supposed to be on the same side. So part of this process in understanding how to work with a question like this is to figure out what went wrong, what needs to be changed, and what makes sense to fix. Okay, and that's, I'm going to admit this, that's something that a lot of people, when they get to a certain point, they just can't handle. And it's like, it's wrong, I don't know what's wrong, I don't know how to fix it, I'm just going to let it be. But you know what a good thing to do at that point would be? Would be to write a little note saying, there's something wrong with this here, I'm not sure what it is, and I don't know how to fix it. As opposed to just continuing on knowing that something is wrong. If you recognize that something's wrong, that's in your favor. If you can tell me that what you did was wrong, as opposed to just doing it wrong. Right? So next time when you take another test and you end up in a situation and you say, this isn't working, this is wrong for some reason, I don't understand it, it's better for you to let me know that than it is just to let it sit there and just know that it's wrong. Okay. So then, once you get to that point, if you do this properly, then you've got the test value is not in the rejection region. And so therefore, we do not reject the null hypothesis. And when I do not reject the null hypothesis, that means there is not enough evidence to prove H1. And this is almost the most important thing ever, right? Because you have to make the correct decision based on the information you're given. Getting the hypotheses is good. Getting the critical value is good. Getting the test value is good. But if you don't make the right choice at this point, that's substantially wrong, because the whole idea is, how do we make a decision once we know all the numbers? So this is really important to make the correct decision at this point. And it's unfortunate, some people made the correct decision here and made the wrong decision there, or vice versa. Okay, so these are supposed to match up. Do not reject, there's not enough evidence. Okay, so again, that's important stuff. And going forward, the next test that we have, you will not have very many calculations. It will be mostly interpreting things. So you need to be able to interpret things correctly. That's very important on the next thing. And to be able to then say, what do we mean when we say there's not enough evidence to prove H1? The summary statement would be, there's not enough evidence to prove that the population mean of La Crosse is less than the national average. That's the thing that we're trying to prove, but we can't. We don't have enough evidence to say that La Crosse waste is a lower population mean than the national. Now, I was a little bit, how can I say this? Lenient, I guess would be a word. If you didn't use the word population, I didn't count it wrong. Okay? But you should have said something about the fact that it was an average that was being used. Okay? And the fact is, it's the population average. If you use the word sample, that's wrong. We're not really concerned about the sample average. We know what the sample average is. The question is the total average of the population of La Crosse less than the national? As we tried to prove, we could not. That's the conclusion. All right, so again, this whole process here, towards the end, being able to make that kind of a correct decision and then say what you're actually doing, that's going to be pretty much a lot of test number 4. So you really need to know how that works and how to express those answers. Okay, so any other, any questions at all about the test? Certainly possible for me to make mistakes when I grade these things, so if I made a mistake, let me know. I can try to fix it. All right, so certainly if you have a question later on, we can talk about it. But for right now, we need to talk about homework set number 14. So we'll go there. We go to the publisher site, and we work on homework set number 14. Hopefully it'll come up with the stuff that we want. 14. Okay. So what is the deal for homework set number 14? The deal is that we're talking about X and Y. We're talking about different observations that have 2 numbers in them. And so these are the things that need to happen with this particular homework assignment. We're talking about 2 variables here. You need to be able to graph points. You're given the points that are on the data set. You need to be able to graph them. And you also need to be able to interpret the correlation, which includes doing a hypothesis test. Correlation. Okay, so we've got that going here. Let's see. Next. 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 And that's what it is. Yep. Okay. The other thing that happens with this is to be able to interpret regression. And what that's going to include is that you're able to graph the line. Okay, now some of you have not experienced this very much. We're going to go through this in more detail right about now. But we're going to talk about what it means to graph the line. And then to be able to interpret the line. Okay. Let's see, I think that's all that's here. Yeah, there we go. So these are the things that come from this homework set. Now, some of you have expressed that you were having some trouble with this particular set of homework. And the fact is that I wanted you to do this homework by using the commands on Microsoft Excel. So that if we were to go to the notes section, I have this thing, how to use Excel for correlation and regression. We went over in class, and that you should use to do the homework. This will not be on the test. You're not going to be using Excel on the test. All the calculations for this will be already done for you as far as finding the correlation and finding the regression. You will need to be able to do these things that I have written on the board, but you will not need to use Microsoft Excel or anything like that on the test. The reason why I wanted you to do it using Microsoft Excel is because when you get out of here, you're not going to have me telling you what's going on, and so you need to use maybe Microsoft Excel to do stuff. And so then when you get out of here, then that would be a helpful thing for you to know. But for right now, what I want to do is to make sure that you understand how to do these things right here so that you can make this work, right? If you're stuck on using Microsoft Excel, it might be that we would have some time after class today, maybe get done a little bit early, if possible. And then at that point, we could go to the computer room and I could show you how to do it. All right? But for right now, what I'm going to do is put some information up here on the board, and we're going to see if you can do the things that are listed here. There we go. All right, so we're going to talk about literacy rates. Well, let me find it. Let's do this one instead. Carbs and calories. Okay, I'm going to write a list of measurements. These are for different foods that are out there. And I'm going to list the carbs and the calories. Then what I'm going to want you to do is I want you to graph these points. Okay? So, All right. I want you to graph those things. I want you to make a little X and Y chart in your notes. These are not to turn in or anything, but I want you to graph those 6 points. Now I'm going to give you what might be a helpful hint. Before you actually make your graph, you should figure out what are the lowest and the highest values on the X and on the Y, and you should make your graph based on that. You don't have to go down to 0 on either of these scales, okay? It's best if you just make your horizontal and vertical based on the data values that you have. You don't have to worry about where 0 is in order to make the graph. All right, check with your neighbor, see what your neighbor's got going on here. All right, you should get something that looks approximately like this. What's going to happen on the test would be something like this. So if you don't know how to do this right now, this is a great time to ask a question and I can help you out. All right? Does anybody have any question about this process and making this happen right now? Question?
How do you know what's X and what's Y?
X is the one that comes first.
Always?
Yep.
Excellent.
All right, any other question about this right here? Okay. So the next thing that happens is that we're going to have the correlation on this. And the correlation comes out to be 0.979. And we're going to do a hypothesis test on that correlation. Okay? So, Haley, what's our first step in doing hypothesis testing? It would be to your advantage to have that sheet of paper where I gave you the steps for hypothesis testing. With that, tell me what step number 1 is. Okay, we want the hypothesis. All right. Lisa Peterson, can you tell me what the hypotheses are for correlation?
It would null hypothesis equals 0.
Nope, sorry. Null hypothesis is a statement about something. What is it that we're talking about? Ms. Peterson, can you tell me what it is?
We're talking about carbon calories.
We are, but when we're asking the question, what thing is in the null hypothesis for correlation? I want to know, what is that symbol right there? Debbie, can you tell me?
We roll.
A little help here from the front row. Yes, rho is the symbol we're looking for. Okay, Alyssa, do you remember rho? Rho equals 0. That's the null hypothesis for correlation hypothesis. Well, Eric, what's the alternative hypothesis?
That's what I was trying to figure out.
Oh.
Be equal to that equals election.
No. Rho is equal to 0. Oh, that's the null hypothesis. I want to know what's the alternative hypothesis. Rho is not equal to 0. Okay, when we're doing correlation hypothesis testing, the null hypothesis, rho equals 0. Alternative, rho is not equal. Okay. Now I want to know what those things actually mean. Danielle Cote, can you tell me what those things actually mean?
So it's a null. So the null is no relationship. And then the alternative is there is a relationship.
Okay, but to be a bit more specific, there is no linear relationship. That would be the null hypothesis. The alternative, there is a linear relationship. Okay? So this is what we're looking for. Whenever we do hypothesis testing for correlation, we're asking questions about this right here. Rho could be 0, but maybe it's not. If it were 0, that would mean that there's nothing going on. There's no linear relationship. But if it's not 0, then that's an indication that there is possibly a linear relationship. Okay. Casey, what's next? Okay, we need a critical value. Now the critical value here is going to come from, I believe it's table I. And we need that information here. And it's in the textbook. And I'm pretty sure it's page 658. Yep, there it is. Okay, so I have this right here, which is critical values for the PPMC. Right? How many degrees of freedom are we going to have right here?
4.
4. There are 6 measurements, so we have 4 degrees of freedom. So what's the critical value? 0.811. What does that look like? It's a two-tailed test. What does the picture look like?
0 in the middle.
0 in the middle.
And then 811 is past there. Negative 0.811 is over here.
What's on the far end?
Which I just thought.
Nope,
One is positive, one is negative.
that's true, but it's a version of 1. Okay, so this would be positive 1, and this is negative 1.
Okay.
Okay.
Oh, okay.
And so then 0.811 would be here, and then like you said, negative.
Yes.
What do I shade in here, Jackie?
You should to the right of the. All right, so you do both the ends.
I do the ends, that's correct. This is my rejection region, both ends here. Okay. This is my critical value and rejection region. Okay. Natasha, can you tell me what I do next? Okay. Alicia Bell, can you tell me what I'm looking for test value here? Okay, so R is 0.979. That's my test value. So Alicia, can you tell me what happens with that test value?
If it's in the rejection region, you reject it. No.
Okay, if it's in the rejection region, we reject the null hypothesis. It's in the rejection region. It's right here, 0.979. So we're going to reject the null hypothesis. Donna, can you tell me what that means?
But there is no evidence.
There is enough evidence for what? Okay, I reject the null hypothesis. That tells me there is enough evidence for what? Brianna, can you tell me? To prove the alternative, okay? So we reject the null hypothesis that says there is evidence to prove the alternative. So Brianna, what does that mean? And what that means is there is a linear relationship. Okay? So when we say we prove the alternative, we prove rho is not equal to 0. In other words, there is a linear relationship. So if we go back to here, I just closed it. Well, if we go back to here and we say, all right, we have a collection of dots. They are not exactly on a straight line, but there is enough evidence that a straight line would be a good understanding of this relationship. Okay? So we're interpreting the correlation as being a pretty strong relationship, and it's positive. Okay? So, Taylor, can you tell me what it means if I have this being positive? Okay, but specifically the data that we're doing, what does it mean?
The higher the carbs, the higher the calories.
Okay, the higher the carbs, the higher the calories. Now it seems to make sense because carbs have calories, but they're not the only things, right? And it's not a straight line, so it's not exactly that carbs make calories. There's more to it than that, but it is related. More carbs, more calories. Seems to make sense. Okay? So that is talking about correlation. Now we're going to talk about regression. Okay? So what we're going to have then is a regression relationship . And it's going to look like this. Okay, this is my regression relationship. Now there are people who get kind of bent out of shape when I ask them to do this, so I'm going to try to take just one step at a time. Okay, I want you to draw the line on this graph. I want you to use this equation right here. I want you to use that equation to actually draw that line on the graph that you made with the points. Now, most people, when I tell them that, they say, I don't know what x value to use. And my answer is, whatever x value works so that you're able to draw that line. It would have to be an x value that's included within our data set, but it doesn't have to be any of these specific points. You could pick 12 for x, put it in here, figure out the y value, and graph that point. And then you could pick 16, put that in there for an x value, and figure out that number, and then draw the line between those 2 points. You could pick 11. You could pick 17. You could pick any numbers that you want to, but it doesn't make a lot of sense to pick 2 numbers really close to each other on the middle of the graph. It makes better sense to pick a number that's relatively low, another one that's relatively high, and then draw that graph using those points. it doesn't matter what points you choose, but you should pick a point that's close to the bottom, another one that's close to the top, so that you can get an idea of where that line is. Once you do that and you draw the line, if it doesn't go through where the points are, then it's wrong. And the process, once again, is that you're taking whatever x value you want to use, put the x value in here, you're going to multiply it by 4.5, and you're going to add this negative number right here. Question?
So where'd you get those numbers?
I got them from the computer.
Okay.
So you are not going to have to come up with the regression equation yourself. I'm going to give it to you, but you're going to have to take this equation and graph it on the graph, which you just did, which has the points on it. All right, I'll give you a couple minutes, see if you can make that happen.
Because that's, yep, you just put it somewhere, so like, maybe like, that's so you'd be like 43, be right in the middle, 24, whatever, 24, 2, you know, just put it out there, where you think 42 is. And then 70.42, which is right about 70. And then I just put it out right here. I could be wrong. Well, you just put it, so where do you have 11? Where do you have 11? Yep. So 11 to be there. And then 43, 54. Oh, I see what you're saying. You were gonna put the dot like where?
Yeah, I'm wondering.
So if you pick 11. Right. Right there. So it'd be like just above this dot.
Right, okay.
All right, you might want to check with your neighbor, make sure that what they've got looks right compared to yours. All right. All right, so this is what it's going to look like, more or less. So, Emily Grenier, what'd you use for X and Y for your thing?
for the bottom, I did 10.
Okay,
And then for Y, I got 38.92.
okay,
And then for Y, or for the top end, I got 18, and I got 74.
okay.
Okay.
All right, that should work. Anybody have any further questions about making this thing happen right here?
Build up the regression relationship.
Okay, so this is the regression relationship here, telling us something. Then the question is, what is this actually telling us? Okay, now that we graphed the line, we need to interpret what this means. Okay? First of all, it's important for us to understand that we cannot believe this line. This line is not true in the best sense of the word. Why do you think I would say this line is not true? Why can we not believe this line? It's not a direct line. The data is not on the line. It's not. It isn't. It won't be. It couldn't be. It doesn't make sense for it to be exactly on the line. This line is not a description of the relationship. It's not. It won't be. It won't ever be, generally, an actual description of the relationship between the numbers. The numbers are a cloud. The numbers are not a straight line. What's another reason I should not believe this? It's based on a sample. I only have 6 measurements here. If I did 6 more measurements, they would be different. This line would be different than where it is. I should not believe that this line is actually telling me a relationship. Another part to this line is designed to actually predict the average, not where things are actually happening, but the average. And even then, it's not correct because it's going to change next time I do it. So textbook, unfortunately, doesn't give you that impression. Textbook says, if it's this for X, what is it for Y? And the answer is, you don't know. You can't know. If you put in an X and a Y and you put them on the line, that does not tell you what's happening. It tells you this is an estimate of the average that's going to change next time I get another 6 months. Yeah. All right. So number 1, we should not believe what this line is telling us. Number 2, what is it actually telling us? Okay, which is what Taylor already said. Taylor, what did you say?
That the more carbs, the more calories.
The more carbs, the more calories. And that's what the slope is telling me. The slope is telling me how fast that increase will be. As I have 1 more carb, I'm going to have 4.5 more calories. But the basic idea is the more carbs, the more calories, and that's this positive number right here for the slope. That's what that's telling me. Okay, question.
So that is the slope.
This right here is the slope.
Oh, okay.
This number here is the intercept, which most of the time doesn't actually make any sense. It's just a matter of locating the line in the right place. But the intercept by itself is often not. Okay, so now we graphed the line, and now we've interpreted the line. And so these are the main ideas that are found on the homework, which was due for today. Okay. So we're going to take our break now, and then we're going to talk about the homework, which is due for tomorrow. So that puts us at 4:06.
Yeah, it really helps me. Yeah. I did.
Do you have my, retest test too?
I do not. I apologize.
Okay, no, you're
But-
good. I just checked the grade book.
Okay.
It's like I thought I did a lot.
Yeah. Yeah, I'll take a look at that.
Okay. I just like.
Yeah.
Yeah. Oh, yeah, I like that one. I'm junior. That's the trash you're saying. A little sneaky. Yeah, it's expensive. You did? Yeah, you can. Same. 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 So,
I was at retail. I didn't put my initials or like the shirt check as soon as this. I know. I just. How did he have to put in there?
we got $1,000. Why?
I don't think that's what
So those are for children. Okay. He said my sources weren't. Yeah, really. He also said my formatting was wrong. I'm like, I'm sorry, I've never written Chicago style. I don't know how to cite Chicago. Would you guys get on that? Well, that was
She's going to give everyone. I know I did that before, but it's like,
I can guarantee you. I was yeah,
I know, but like I literally
I kept looking at it, I was like, oh my god, like where did the bone go? Like it legitimately looked like the bone just got ripped out.
how did you do it?
It just said an ECG accident, we didn't really know what happened, it just ended up awkwardly. That's one of the comments that I read, I don't know.
Oh, that's what happened. I just like looking at it, so I wanted to see if I knew it. She was in the like, what I would do to like, I would definitely hack GI. Just like clean up the packet, grab it.
Can't imagine, like, they're ready for Kobe.
What could she get on?
She said she can't put any weight on it for that school.
Like writing sheets.
Well, I assume so, still.
Sure. There are things where we don't have to.
But still, like,
Yeah, you don't
you
want to mess with
can't do like.
Oh, hi.
Like bombarded.
You're scary. Come on.
I just want to know if we can retake our test next week. Number 2.
Yeah.
Like next Wednesday.
Sure.
10:30?
10:30? Yeah, well, send me an email.
Yeah, okay. Sounds good.
But that's, yeah, that's fine.
Okay, that's perfect. Wait, thanks.
Mhm.
Yeah, I heard real bad. No, that was a crash. I can't get it. The heel to like some kid tried to like, I'm gonna burn you. Get my thumb on fire with like a lighter. Trying to laugh. I was like, man, it's not gonna happen. Really? I love it. Oh, so cute. Yeah. Is that one? Yeah. I take more of like a severe.
All right, well, let's try and make this next set of things happen here. Okay. So, I'm going to try and follow these notes that I have here, but I'm not going to be referencing the textbook very much because people don't have the textbook in front of them, so I might as well do something else. So we're going to do this. So when we say, what does regression actually give me, right? Regression is supposed to give me a line. But I've just made a big deal about the fact that the line is not really what's happening. If I say, what is the relationship between carbohydrates and calories? I really don't know the data specifics because this is telling me about an average, and I really don't know that because it's a sample, right? So what I want to do then here is to be able to say, what can I know? Right? What am I able to get from regression? And what we're going to do is we're going to think about this, and I think I've got this in the textbook here. Ebook. Here we go. So let's go to relation regression. Regression. Where is that graph? It must be in the previous one. Well, there it is. Okay. What are we actually assuming here? What we are assuming is that it's not just that we have straight lines. What we are assuming is that every measurement that we make is like a bell-shaped curve. Okay? But it's a bell-shaped curve that's sitting on a graph, not just one bell-shaped curve, but it's a bell-shaped curve that actually moves. So that if I have a low value of x, my bell-shaped curve is low. If I have a higher value of x, my bell-shaped curve is up higher. Okay? So we're thinking that we have all these bell-shaped curves involved when we're doing these measurements. So then what we're really talking about is a cloud. Right? Let me show you a cloud. This is a measurement of the age of a person and their blood pressure. There are 4,500 data values on this graph. Okay? And you can't see them because they're on top of each other, but there's like a whole bunch of points right in here. They're all just on top. And so if we were looking at this right here, if we did like a histogram of this or whatever, this thing right here would be bell-shaped. So with this thing, it would also be bell-shaped. So with this one, it would be kind of bell-shaped. All the way up here, we have this big collection of bell-shaped curves. This bell shape has its center about right here. This bell-shaped curve has its center about right there. Is the center going up? Is that line, this red line here, is that line going up? Yes, it is. So what does that tell you? That tells you that on average, older people have higher blood pressure. But it does not tell you that if you're old, you're going to have high blood pressure, and if you're young, you're not. People who have 150 here could also have 150 over here. Okay? So just because you're young or you're old, that doesn't tell you what your blood pressure is. But it does say that on average, your blood pressure is increasing when you get older. From what? 115 to maybe 125 or something. It's not a huge difference. But it is increasing. So then, what we want to do when we're thinking about this thing is that we're going to be thinking about confidence intervals. For each X value. So the different X values that are, I'm sorry, confidence intervals for Y for each X value. What are we measuring? Y. How do we measure it? X. I know somebody's age. I want to predict their blood pressure. That's what's happening here. But what I'm going to do is I'm going to have a confidence interval. It's not going to be an exact formula. It's going to be a confidence interval for the thing. So now let's go back to our carb situation. Okay, here's my line that fits them. But what I'm going to do is I'm going to change this so that it will have a confidence interval. So now it looks like this. And I need to put my lines on here. Graph properties, horizontal lines, vertical lines, yes. That's better. All right. So what I'm going to do for a confidence interval is I'm going to say for carbs equal to 12, what is the confidence interval for the calories? Okay. So what I'm going to do is I'm going to come over here to this graph, and I'm going to look where it says 12. Here's the line 12. Here's my line 50, 40, 60. Right? So these green lines are showing me the confidence interval when X is equal to 12. What would you consider this number to be approximately? What Y value would that have? Could be 45, 44, 43, somewhere in there, right? So 44, let's just say. So if X equals 12, the confidence interval, bottom end is 44. What's the top end? What's this number? Oh, Jackie, you're too fast. 51? Sure. Maybe 52, somewhere in there. 51, let's say. Now, what is this confidence interval talking about? This is talking about the mean of Y. Mu of Y. For X equals 12, mu of Y is between 44 and 51. What that tells us then is if I have 12 carbs, the average will be somewhere between 44 and 51. It's not telling me where my data values are, it's telling me where the average is. So my average is somewhere between 44 and 51. Okay. So the number that I have for my formula, if I put in a 12, I got some kind of a number for the calories. That's not the real average. My actual average is going to be somewhere between these two numbers, 44 and 50. So if I took all the food out there that has 12 carbs, and I said, how many calories is average for those things? The average is between 44 and 51. That's what this is telling me. Confidence intervals are telling me something about a population from the sample. This is telling me the average of all the carb things that have 12. This would be the average amount of calories. That's the confidence interval. But then there's something else that we haven't done before. It's called the prediction interval. The prediction interval is for data values for each x value. Data values of y, sorry, for each x value. So I'm going to revise my previous statement. Confidence intervals are for average y. Prediction intervals are for data values. So now I'm going to make prediction intervals. Prediction interval. Okay, now Jackie, you can't answer these because you're answering. Here's 12. Here's 50. Here's 40. Here's 60. And now I want to know my prediction interval. That's going to be here. So if x equals 12, what is my prediction interval? Who's going to volunteer, now that Jackie's out of the running, to tell me what these numbers are? 41? And what about the high one? 56 or 55 or something like that. But what is the thing that's in between here? This is actual data value. It's not the average anymore. What we're going to be able to say in this situation is if it has 12 carbohydrates, this will actually predict the number of calories that the food has between 41 and 56, not the average. This is actual data values. So this is telling us what to expect from the data values themselves. This is really big deal for us because if we're able to do this, this is going to help us to know what's going to happen and what would be unusual in a specific situation. I could say, hey, look at this food. It's got 12 grams of carbohydrates. But it's got 70 calories. Wow, that's big. Whatever's going on, this thing is loaded with calories. Because it would be unusually high if it's outside this prediction. Again, the confidence interval is just telling me about average, but the prediction interval is telling me where I should expect the data values to be. Okay, so let's do another one here. Let's go out here to homework set 14, which we already looked at. Do I still have that up? No. Okay. So homework set 14, preview. We're going to talk oil and gas prices. Yay. And again, I'm going to do this for you. You're not going to have to actually do the calculations. I'm going to give you the numbers, right? Or the graph, either way. Okay, so go back here. The new one. Here we go. So now we're talking oil and gasoline. And I'm going to do just what I did. Oil, gasoline. And I'm going to do these two things. Now, does it look like we have a line? Well, kinda, all right, it looks kind of like a line. If we go back here, we do have an equation for it, and it does come out to work. It's 0.841 for correlation. So if we look at this, and I say, what is this point? Okay, oil was at 52 and gas was at 295. How would I describe this situation? Well, when I look at this right here, here's my confidence interval. The confidence interval is telling me about the average. This is where I expect the average to be. So would you consider this point to be a little bit on the high side? Yeah, it's almost above where you would expect the average to be. So you would say, well, this is a little bit high. It's kind of above average. But compare that to this. This is where we expect the data to be. Would I consider this to be an unusual value? No. It would have to be way up here or way down here in order to be considered unusual. This is to be expected anywhere in here. Now, let's think about this. I want to predict the price of gasoline. And I know that the price of oil is 52. X is equal to 52, and I want to predict my Y value. It's going to be somewhere, oh, I should put the lines on here. It's going to be hard to see without the lines. horizontal, vertical lines. There we go. Okay. So my data value is going to be anywhere from what? 2.5, 2.6, 2.7. Going to be everything from $2.30 up here to say $3.20. If somebody's trying to predict gas prices, and they say, well, gas prices are going to be somewhere between $2.30 and $3.20. Is that a helpful prediction? I'm driving around a lot, and somebody says, well, gas is going to be somewhere between $2.30 and $3.20. Is that going to help me make a decision?
Maybe 5. Something on the lower end.
Yeah, but it's not really that helpful because you don't really know what's going to happen. It's somewhere in that range, but it's a relatively wide range. Okay. So this is what the challenge is. If you ever see a straight line graph, don't believe it unless it has these confidence intervals and prediction intervals on it. The confidence intervals and prediction intervals are actually telling you what to expect from the data. If you just see a straight line, that's not telling you what's happening. But the confidence intervals and prediction intervals do actually tell you what to expect. So if I say, can I predict gas prices from oil prices based on my data? Well, I can, but not very accurately. There's a pretty wide range. So let's go back to these blood pressure things. If I know somebody is, let's say, 30 years old, can I predict their blood pressure? Well, it's somewhere between like 85 and 140. Well, that's not really that helpful. But what if somebody is 70 years old? Can I predict their blood pressure? Well, it's somewhere from 90 to 150. Okay, that's not a whole lot different, right? If I compare the young person, the old person, there's quite a bit of difference in the data value. So, does age tell me blood pressure? No. Are they all on a straight line? No. Is there something happening here? Yes, but it's relatively small, and it doesn't really change my prediction of the actual blood pressure. So these prediction intervals are telling you where the data is actually located in the cloud right here. But what about these people that are above the yellow line? Wow, they're definitely high blood pressure people. But you know what? There's people below there too. These people are unusually low in their blood pressure. These people are unusually high. As it turns out, there's more on this end than that end. So there's more things that make people have high blood pressure than low blood pressure. But that's a different story for a different day, right? All right, now we're going to talk about a couple of other things. Hopefully. And this is when we're talking about R and how strong it is. I'm just going to tell you this, and you're going to have to believe me. Oftentimes we use R squared. And this is the strength of the relationship. Remember that we said if R is +1 or -1? Well, a lot of times in statistics we use R squared, not just R. And so then it's just between 0%, and 100%. Okay, so we square R and then we make it into a percent, and that tells us how strong the relationship is. I'm just going to put that out there because it works for both negative and positive things. You just square the value of R and you express it as a percent. So for example, what about the carbs? R squared is 71%. So the carbs and calories is 71%. So that's pretty strong, right? When you say, if I know the carbs, how strong is the relationship with the calories? 71%. Well, that's decent. It tells you a lot. Okay. But what about those blood pressure people? R squared is 32%. Age and blood pressure, 32%. So if I know somebody's age, that tells me something about their blood pressure, but it's not as strong. It's a 32%. Now I'm not going to go into detail about why that is, but you'll see this. Obviously, what I'm doing here, I'm using a computer. It tells me R squared, and it considers that to be important. So that's what it means. All right, so we've got R squared, we've got that. What's the other thing we need? Oh, haha, yes. Let's go with versus statistics, data analysis, keep, continue. Oh, great. Thanks. Didn't want to do it for me. Crazy. So I'll use the one that I've got here. There we go. Here are the times for women's 100-meter sprint record. And we're going to do this. There we go. Where did I get that? Vertical axis. No. Chart type. Yes, yes, yes. Computer doesn't want to do it for me. Oh, there we go. Trend line. Yes. Okay. According to this, as time goes on, people get faster when they run 100 meters. Okay? So far? Well, we don't have to necessarily draw a straight line. We could try drawing a curved line. Does that curved line fit the data better than the straight line? So I'm like the eye doctor. You like number 1 or number 2? Do you like this one or do you like that one? Does number 2 look like it's closer to being in the middle? Okay. Well, it also has a higher r squared value. So it is a stronger relationship mathematically. It's closer to that. Well, what about this number 3? It doesn't look a lot different, does it? How about number 4? Oh, looks kind of interesting. How about number 5 or 6? How about that? Does it look like that goes through the points? It does go through the points, but it kind of goes crazy, right? Way up here, way down here, all over the place. It goes through the points, but it doesn't seem to make any sense, right? It's bouncing around a lot. So I'm just going to tell you this thing, what's called nonlinear regression. How do I know if something is a straight line or a curved line? Well, one thing, I could compare the r squared, but another thing is I just have to look at it. I have to see what it looks like. This is something that's really important in statistics. You should actually look at the data. You should not just trust what the computer tells you about a number. Because if I use this polynomial with 6 degrees, I have this weirdo curved line, and it says it's better than a straight line. But it's not. It's crazy. Now, one more thing that I want us to talk about, and this is curve fitting for high temperatures. Okay. This is January. This is the normal high temperature in January, 25 degrees. We are almost here in August. The high temperature for July and August is about 82. It's actually a little bit higher in July, 84, compared to August, which is 82. Then it goes down. I don't know if you know this, but it gets cold in December. In January, it's even colder. But do these fit a straight line? No, doesn't make any sense to say it fits a straight line. So what I did was I predicted these lines using a formula which uses trigonometry. So if you've done any trigonometry, in order to predict the high temperatures for the different seasons of the year, use trigonometry for that. So you might see them on your calculator, right? Sine, the cosine, the tangent.
We're not going to do that.
We're not going to do this. But it is possible for you, just by shifting things around and squeezing things together and making them farther apart, you can actually go through it. It's not hard, really, once you understand how to graph things using these formulas. It's not hard to actually come up with this graph. So that the temperatures in La Crosse, on average, are very close to these trigonometry things. And so when we say nonlinear regression, it's not just straight lines, it's not just weirdo lines that bounce around. It's anything in mathematics. Things like logarithms, things like fractions. You can have y is equal to a plus b over x. You could put x in the denominator. You could have the cube root of something. You can do anything. And so this is what a lot of scientific people are working on, is that once you do a bunch of measurements, how can you predict them? How can you actually come up with this kind of a formula? And if it's not a straight line, what are you going to use? And it's not easy to figure out sometimes. All right, so what's going to happen on the homework for next time? it's gonna look like this. Okay. No trigonometry. Okay. What I have are two different situations. You can see the data values here. And this is using a straight line and it has all the information about the regression up here. But this is using a curved line. And so what I want you to look at and try to think about which makes more sense. And then how would you know? So that's, you know, it's just a thinking question just to have you look at it and think about it. Then this one, this has the federal spending compared to how many motor vehicles get stolen. Is it true that the more federal spending for a particular state, the higher motor vehicle thefts are going to be? So I want you to look at this. I want you to look at the R-squared, and I want you to look at confidence intervals and prediction intervals. Confidence intervals would be the red ones. Confidence intervals are the blue ones. Prediction intervals are the red ones. Okay? And that's it. That's all you have to do for Wednesday. Okay, so we're done. We're going to stop right here.
You said confidence intervals are blue?
Yes. And prediction intervals are red.
And I wish I knew why I got so hot in the first.
I better say this time to do a shop. I haven't since like weeks. So we literally have like old milk, eggs, applesauce, and like sauces. Like our fridge is so sad. So it's time. I don't want to do it, but it's time. Yeah. I like it, but I just like don't have a lot of oh yeah, I want to I gotta go back to my old prudish ways. Seriously. Especially when everybody's free and like I don't have to like after they do that. Right.
Donna, don't forget your phone.
So I'm not going to be here on Wednesday. I have a work training.
Oh, okay.
Should I just like try to give you the homework or email it